My name is Venkateshan, and I'm a data scientist in the logistics team at Flipkart. And the title of my talk today is Solving the Vehicle Routing Problem for Optimizing Shipment Delivery. Great. So, so when you order an item on Flipkart, the order goes through multiple stages. Right? If you look at the physical movement of the item, then it gets dispatched from the warehouse, hops along a series of sorting centers, and finally lands at the delivery hub. Now, at the delivery hub, you have a wishmaster or a field executive who basically carries a subset of the shipments and then follows a path and delivers the shipments to the respective doorsteps. In a typical hub, there's somewhere between, say, 300 to over 1,000 different shipments in every shift. So that's not only is it a large number, but it's also there's quite a bit of variability there. So now we pose the question: given a set of shipments at a given delivery hub and a set of FEs who are going to go deliver it, A, what should be the allocation of the shipments to the different FEs, and B, what should be the specific path that they should take to deliver their shipments. So that's basically the problem we're going to be talking about today. Before I delve further into it, let me give you the wider context. Where is this applicable? Now, it's applicable to any business where there is delivery of predetermined shipments at specific locations. So, in addition to say e-commerce companies, it's also say, for instance, like your online grocery ordering, as long as the shipments are determined beforehand. And most of B2B planning and scheduling most likely also happens that way. Now, to me, though, the canonical example is the postal service. You have parcels destined to different addresses at a post office, and you basically have a bunch of postmen, and so you need to distribute that among the different postmen, and you need to determine what should be the best route that they should take to deliver those parcels. And obviously, postal service has been there for much, much longer than, say, for instance, like e-commerce companies. Okay, now I want you to contrast that with a different situation where you have on-demand delivery. Classic example of that is like online food ordering, where the assignment or the delivery planning has to happen on the go. You place an order and you probably get your food in 40, 45 minutes. So the assignment and all the other routing should happen, say, decision should happen, say, within 15 or 20 minutes. That's true with cab aggregators as well. So the sort of methods that you use over there is slightly different from the one that we're going to be talking about. Now, there are different ways to basically, there are different aspects on which these are different. But to me, at least, one aspect which basically, one axis by which I would separate these two things is that in the case we are talking about, there's nearly full information. There is problems with, say, getting hold of travel times, traffic, and everything. Leave that bit out. But there's near complete information. Whereas when you talk about, say, something like on-demand delivery, there's only partial information. You don't know where the next where the next demand is going to come from. You don't know how much it is, and you don't know all the other parameters associated with it, right? So that's the sort of the critical separation between these two things. So let's get back to what is typically done in these hubs. It's a manual process, right? So you have the delivery hub and you have a set of shipments. So the delivery zone, right, that is the region over which you accept shipments for that delivery hub, is divided into different regions. The zone is divided into different regions, and then shipments falling within each region is assigned to an FE who's most familiar with it based on experience, right? And then he goes about and delivers the shipments. Now, clearly, this is an inefficient process. One, it takes time to sort these shipments into these different regions. Two, you can have like wrong assignments to FEs. And three, you basically could have, and in fact do have, an asymmetric assignment. That is, some of them end up getting too many shipments and some of them getting too few, right? So we want to basically do something about it, right? And it becomes all the more difficult when you have customer time windows. Because you promise to deliver the shipment within a time window, and you do that for all the customers, then sort of manual planning is even harder, right? So we want to automate the process, right? So how does one automate this process? As you can imagine, the automation process is you achieve that with some sort of an optimization. Now, what is this? Well, just like in any other optimization, you have a configuration, in this case, a configuration of routes. And for that, you associate a cost function, W, and an appropriate cost function. And then you try to find the route, the configuration, the set of routes, which minimizes that cost function. That's the standard optimization problem. Now, what is that appropriate choice of the cost function? In the classic formulation of this problem, it is the total travel time. Right? We won't go ahead, we'll have to make some changes to that, but that's a classic formulation. Then when you have only one agent delivering all these shipments, right, with this being the cost function, you recover the classic traveling salesman problem that you probably studied in computer science. Now, if you also recall the details of the traveling salesman problem, it is NP complete. And this is a generalization of it. So this is also NP complete. Couple of technical points. The TSP is NP complete because the Hamiltonian path problem is NP complete, to which this reduces to. Hamiltonian path is trying to find a cycle in a graph. And the other point is that it's NP complete in the sense that when it's posed as a decision problem. The decision problem is basically given an X, does there exist a solution such that the total travel time is less than X? In that sense, it's NP complete. And this is NP complete as well. So even though this is a difficult problem, there's been plenty of work done. In fact, it's been exactly 60 years since George Danzig published the classic the truck dispatching problem, 1959, in which he introduced the VRP. Great. So let's talk about some variants of it. One is that, like I hinted earlier, you have customers who promise time windows, and so you want to make deliveries within that time window. You want the arrival times to be within that time window. So these are known as vehicle routing problems with time windows. The other thing is that capacity constraint. You have the vehicle or you have the FE, and there's only maximum number of shipments you can carry or maximum volume. So when you have problems like that, you have the capacitated vehicle routing problem. And when you have both constraints, customers with time slots as well as like the capacity constraint, you have the capacitated vehicle routing problem with time windows. Now, as you can imagine, this is not some sort of an academic variance, right? In real world situations, you'd prefer, as a business, you'd prefer that you give a time slot to a customer. You don't let the customer wait the entire day. You'd prefer, all else being equal, that you give them a specific window and you deliver it. Likewise, the capacity is a natural constraint. You can only carry so many things in a bag or in like in a vehicle or something, right? So these are very real world sort of constraints. Great. And so we will be talking about the last one, the capacitated vehicle routing problem with time windows. Now, we actually have a custom solver, but I just want to quickly say why we need a custom solver. There is an existing solver that we're using, which is the Optaplanner, a Java package. The problem is that, one, in the results, it tends to give overlapping routes, which we'll see at the end, and or the routes tend to be elongated and stretched out. But to me, at least, the more significant problem is that the lack of flexibility, right? I can't probe the details of the algorithm properly. I can't quite understand how the change in the heuristics leads to sort of differences in routes. So that leads to a problem of actually understanding what is causing what, right? Because you just give it and then it's like a black box and then you sort of get the output. So I've also looked at, and Java is not a great language for these things. I've looked at like Python variants, and so a couple of them are the local solve and Google OR tools, but neither of them can support custom penalties. And we'll see what custom penalties are. So we have to have a custom solver here. Great. So now I've set up the problem. Let me just give it a slightly more formal touch, right? What is given is the following. You have end customers and the depot or the hub. I use the term synonymously. End customers at depot, and you have their location, xi, y, the latlon. And then you have the pairwise travel time matrix between every pair of them, including the depot. And then you have the serviceable time window for each customer, right? And you have the M vehicles, each with max capacity Q. This is what is given to you. What you need to find out are the routes, the M routes, Ri, are going from 1 to M, such that the following conditions are satisfied. Each customer is basically serviced by exactly one route. 2, the constraints, the time window compatibility, that is, the arrival at a customer should be within its time window, and the capacity of the vehicle, the constraints. Given these things, you want to minimize the cost function. This is the problem. A bit of terminology, you consider solutions feasible if the hard constraints are satisfied. That is, regardless of the cost, it's a feasible solution. The hard constraints, if we call them hard constraints, right, are satisfied. Great. So now I said cost function. I already hinted that it's not enough that we have the travel time. The classic thing, like I said, is basically the classic thing is the travel time. But then in our situation, we need more, right? We have to define new penalties. We have to come up with new ways to define new penalties. One of them, like I said, is uneven distribution of shipments. We don't want, some of them getting too many and some of them too few. So when that happens, when there's a skew, we want to penalize the solution. Likewise, we don't want too many outliers. So we want to minimize or ideally make them zero, right? We don't want any outliers, preferably, or at least reduce the magnitude. I'll minimize the stretched or the extended routes. Okay, so let's take each one of them. The cost, the travel time, there are 4 of them. First one is the travel time, straightforward. You take every single route, and then you look at every successive customer, you sum up the travel times, right? So that just gives you total travel time. The next is the fairness. So that what you define a cost that's proportional to the standard deviation of the distribution of shipments across the M routes or the M vehicles. Right? But then you want to sort of normalize it, so you divide by the average number of shipments, which gives you the coefficient of variation. But there's yet another normalization, which is the square root of the number of customers. And that normalization is basically take care of the fact that when you're considering a different situation with more number of customers, all these cost functions scale uniformly. Travel time, all else being equal, if you just increase the number of shipments, keep the delivery zone, everything else constant, the, the typical travel between pairs of between the, when you have total travel time, that scales the square root of n. So we want all the other things to also scale a square root of n. But if that point is kind of missed, that's okay. That's a somewhat secondary thing. Now the outliers, right? Now before I define the outliers, I kind of want to give an intuition to this, right? It's based on the neighborhood distance. I have two cases. Look at the top right-hand corner, and you have a set of points, and you have one point that's encircled in red, and that clearly is an outlier. Now in cases like that, practically any method will be able to identify the outlier because it's a fairly straightforward case. A more realistic situation is what is below, right? Where you have a patch of points, and then again you have a set of like 4 or 5 points encircled in red. Now that is not as easy, right? So when we think of like methods to determine outliers, we need to take care of these kinds of ambiguous situations. And to be clear, that's not even the most ambiguous. But just to tell you that, okay, you need to take care of these sort of the trickier situations. Here's the actual definition. What we do is that we take a point and then we sort the distance of all the neighbors, and then we take the alphath percentile of it. So there are 100 neighbors, 100 points, you have 99 neighbors, say you take alpha to be 20 percentiles, you take about the 20th nearest neighbor, and you do that for every one of the points. You take the median of it, and then you take the median absolute deviation of it. And then you define like a modified z-score, which is the value of that alphath percentile of nearest neighbor minus the median divided by the median absolute deviation. It's not the actual z-score because that's the mean and the standard deviation, but this is a modification of it. So that's how you define your outlier. Finally, your compactness. We don't want routes to be stretched out or elongated, so we want to keep them relatively compact. So again, we take a similar approach. What we do is that we take a given point and we look at, say, for example, the 80th percentile. That's just, there's no God-given truths about these things. It's just something to get a sense of scale. It's 80th percentile of the solid distance of all the neighbors, right? And so you have those numbers for the cases on the right. If you imagine a set of points over there, the numbers represent the distance, the 80th percentile nearest neighbor, right? And then you get a collection of numbers, and then you basically take the 80th percentile of that. That gives you a number, in this case 1.35, which is a one-dimensional characterization of the spread of the route. So we put them together. We have the travel time, we have the fairness, we have the outlier and compactness. Only the first one is used in typical solvers. So we have to sort of come up with these things to basically account for the situation that we have. Now let's jump into the algorithms, right? Now broadly there are two broad classes of algorithms. One is the exact algorithms, which will basically solve the problem to optimality, right? In principle, it may take longer for it to solve than for the sun to run out of nuclear energy. That's possible, but in principle, it's going to take you to optimality, right? And we're not going to do it, obviously, because it's computationally expensive. So this slide is mostly for information purposes. I'm really not even going to talk about it. If I did, 2 days may not be sufficient for this. So it's just there for, in case you want to look at the references. So what we actually do is basically the approximate algorithms, right? And so here, in the case of approximate algorithms, even in principle, they need not converge to optimality. That's important to remember. There's time constraints and everything, but even if you let it to infinity, it need not necessarily converge to optimality. Great. So now, typically, not always, the approximate algorithms have two phases. One is the construction heuristic, where you construct an initial set of feasible routes, and then you have the improvement heuristic, where you basically take each of the routes, and then you reshuffle them, and then you iteratively improve upon them. And we'll go into each. The construction heuristic. Now, as the name suggests, you start with just the hub initially, right? And then you start generating these routes. So at any stage, what you have is a set of partial routes with some remaining unrouted customers. Say you've routed, there are totally 100 customers, you routed maybe 20 of them, you have 80 remaining unrouted customers. That's a given stage in the construction heuristic. Now, what do? You have say 3 routes and 20 customers inserted. You pick each of the 80 unrouted customers, and then you consider all possible insertion locations. And if it's feasible, I'll define that in a minute. I haven't defined it yet. I'll define it. If it's feasible, I compute the cost. right? I look at every location. If it's feasible, I compute the cost. So let's take a slight detour. This part, like the next few slides, may be a little bit more. You might have to pay a little bit closer attention because it's like it's a sort of there's a continuity here. So imagine there's a partial route, and U and W are the successive customers on that route. And let's say that you're trying to insert a customer V between those two customers, between U and W, which are already on a partial route. Let's say the time windows, updated time windows of U and W are 12 and 12:15, and 12:45 and 1300. And let's also say the service time of each customer is 10 minutes. Let's say that V, the original time window is promised to the customer is between 12:30 and 1400. Okay, this is the situation. So let's say that the travel time between U and V is 25 minutes. So the earliest you can get to U is 12, and you need 10 minutes to service U, which is 12:10. Takes 25 minutes to get to V, which is 12:35. So the earliest you can get to V is 12:35, right? You do a similar computation here. If you assume 30 minutes to get to go from V to W, you need to get to W latest by 1300. So there's 30 minutes of travel time, 10 minutes to service V. So the latest you have to leave, depart from V is 12:20. So think about it. From the previous customer, you find that the earliest you can get to V is 12:35, and from the next customer, you see the latest you can depart without breaking the feasibility constraint is 12:20. So clearly, this insertion is infeasible. But you don't stop there. Let's take a slide. Let's tweak things around a little bit. Instead of those original numbers, let's say it's 20 minutes and 17 minutes. If you redo the same computation, you'll actually find out, in fact, this is feasible. The early is 12:30, latest is 12:33. But notice something. Your original time window was 12:30 to 1400 for that customer. It shrunk down to 3 minutes. So window shrinkage is a critical thing. So you have to keep updating the time windows as we keep inserting customers. Not just the customer that you're going to insert, which we'll see next. Let's go ahead with this, right? Let's say it's 12:20, 12:33, we insert that customer. It doesn't stop there. If you look at W, it takes 17 minutes to go from V to W. The earliest you can start from V is 12:30 plus 10, 12:40. So the earliest you can get to W is 12:57. Now, originally the window was 12:45 to 1300, 15 minutes. It shrunk down to 3 minutes, right? So not only if you did the computation for you, you'll get the same, and you'll get the same result. It shrunk down to 3 minutes. So not only is the time window of the customer you're going to insert shrunk, but also the time windows of the neighboring customer. And in fact, if you repeat this, if you continue with the succeeding and the preceding customers, the same thing happens. But I'm not going to discuss that. Okay, so time window shrinkage. If there's one takeaway, if you didn't follow this so far, it's that you can have infeasible solutions, infeasible insertions. You will, in many cases, not necessarily all, time window shrinkages, most of them at least. Okay, let's get back to the algorithm, right? So we go around, we look for feasible points, we compute the cost. Then what we do is that we compute the minimum cost for each of the unrouted customers. So if they're VS unrouted customers, we compute the cost for all of them, minimum cost. And then these are the insertion locations corresponding to the minimization of the cost. And then we choose the minimum of the minimum. We insert the customer, which takes a minimum of all of these insertion costs, and we insert that customer and at the insertion location given by that. Okay? That's the approach. What's the computational complexity? Number of unrouted customers versus order of n. So you have to iterate over all the remaining unrouted customers when you're trying to insert one customer, which is again order of n. It decreases, but it's order of n. And then again, the cost for checking out each possible insertion location is again order of n. So it's order of n cubed. Now, if I were to stick with this order of n cubed, I can barely solve like 100, a route with 100 shipments, or a route planning with 100 shipments. So we have to reduce it. So we'll come back to that later. So I haven't yet defined exactly what the cost is. I just said we had to compute the cost. But as you can imagine, I defined the total cost I'm trying to optimize. So it's natural then that the insertion cost would take into account, for instance, the increase in the travel time, right? The decrease or increase in the fairness in the uneven or evenness of the distribution. It will take into account whether the new customer that's inserted becomes an outlier or whether the compactness is increased. It contributes to the compactness. This is to be expected. And yet, it's not just, we don't stop there. We also associate a cost with the time window shrinkages of that customer as well as the preceding and the next customer. Now, this should be surprising because our total cost function is this, which I just showed you. It's fairness, compactness, outlier, travel time. There's no extra points for having wide time windows. And yet, when I do the insertion, I'm taking into account the time windows. I'm giving penalizing cases where it shrinks the windows too much. Why? Well, the argument is that if you're looking at purely a greedy process at each step, a sort of a locally greedy thing where you're just looking at optimizing the next step, then yes, we shouldn't be considering it. The thing is that as you narrow the windows, as you narrow the time windows, your future options in terms of search space narrows. Let me demonstrate that with an unrealistic example, but just to sort of drive home the point. Look at this case. You have a hub and you have a set of customers, and those represent the time windows of those customers. Look at it carefully enough, you'll find that this is the only sequence that you can visit those customers. Anything else is going to break that, is going to violate the time windows. What this shows is that when you basically make time windows narrower and narrower, your possible search space, future search space gets narrowed. So you want to basically prevent that, or you want to basically penalize that. You prefer an insertion which doesn't cause that. So that's why you take into account the time window shrinkages as well. Great, that's the construction heuristic, right? So let's talk about the improvement heuristic, the second phase, right? How do we improve? So you've constructed a set of initial routes, and so you want to improve them. And typically the improvement is some sort of reconfiguration of the routes. Either it's an inter-route between routes, you do some you do some shuffling, or an intra-route reconfiguration, right? So it's move or switch customers within a route, change the direction of travel over a route segment, or merge and split pairs of routes. This is certain. But then these are general methods. We are going to jump quickly into what we actually do, right? Which is again has two subphases. The first is the ejection phase. So what you see here is a set of points within a dash circle, and those points get ejected from their respective routes, and the routes are closed, which is the second figure. You see those ejected points. In the reinsertion phase, we take each of the ejected points and then we reinsert them. That's the method, and you can see the first figure and the third figure are different. You get different routes. So you're basically doing some reshuffling, which is the intended objective. Now, more details. How do you eject it, right? There are three different ejection modes. One is a radial ejection where you pick a customer at random and then you eject the B nearest customers. The other one is just you pick B customers at random and you eject them. The first two methods are from this Ruin and Recreate paper by Shrimp. And we introduced a third method, which is the eject B of the costliest customers, where we again have to define what a costly customer is based on those cost functions that we defined earlier, right? And B is again chosen chosen randomly between 0 and F is some fraction times the number of customers in the route. Now, one thing I should mention, which I probably should have mentioned earlier, is that if you think about it, the construction heuristic in some sense is nearly purely deterministic. Everything about it is just you have to minimize something, and then if you repeat it again, you get the same thing. The improvement heuristic is by definition highly stochastic. You pick customers at random. The number of customers that you pick is also random. So there's randomness everywhere. Great. So the reinsertion, right? So how do you what is the reinsertion order? This is important because the order is very, very critical. If we basically maintain the same order, it's very likely we might end up with the same route. We're not making any change at all. So the reinsertion order is based on minimization of the travel time and the window shifts to the nearest neighbor, both of which we saw. And then the actual insertion process is the same as the construction heuristic, which we discussed earlier. Now, what's the computational complexity? The number of insertion times the number of customers to insert times the all possible insertion locations, which again gives me something that's n square. Again, we have to do something about this. Okay, we'll come back to that. Now, I told you, well, the ejection and reinsertion is a method to reshuffle the customers and the routes, right? There's no guarantee that the cost is necessarily going to decrease. In fact, it could, and it does increase. And if we take a purely greedy approach, we're going to say, well, if it increases, then we reject it, and we go back to the previous step, reset the configuration, redo it again. We don't actually want to do that, right? Because we want to sort of explore the possible search space, and we want to avoid getting stuck in a local minimum. So what we do is this technique called simulated annealing, which is sort of inspired by statistical physics. And so what you have is that you say that you will accept something in the probability that's given by you see e raised to minus delta u over t. The t is again a hangover from physics. It represents the temperature, but here it's a parameter which, in some sense, tells you like how tolerant you are to increases in the cost. So t is greater, you accept higher values of delta u. Specifically, what you do is that in simulated annealing, if you have 100 iterations, you start with a large t and then you make it go to 0. Exactly at t equals 0, you recover back your greedy solution. So in a certain sense, and only in a certain sense, it's not a literal thing, is that you're sort of initially looking at the possible you're exploring more because you're more tolerant towards increases in cost, and then you're heading towards like exploitation, right? Towards like you identify what you think is the best case, and then you sort of you're looking at you become more and more greedy there. That's the idea. Okay, the computational cost. I told you we can't. This is not really acceptable, right? So how do we reduce it? Okay, in the construction heuristic, we don't look at. I said we have to look at every unrouted customer when you're trying to insert one customer. We don't quite do that. We pick only the L of the L customers which have the lowest cost as determined by the previous iteration, right? And then that brings it down from N to L, the first step. The second thing is that we narrow the list of feasible insertion points by using the time windows. So before we even explore it, we say that, okay, if this condition is violated, so we're trying to insert a customer between customer V and I is a customer before that. If this condition is not satisfied, then certainly the insertion is not feasible. So we can do that check. And then instead of considering all the insertion points, we look at only G nearest neighbors. Okay, that basically brings it down from L to basic from N cubed to LGN. And L is about, say, let's take a typical case. N is about 1,000, right? Or 500,000. Your L and G would be something like, say, 20 of 40. L would be about 40, G would be 20. So you're essentially bringing it down like 2 orders of magnitude. And then if you look at the performance, you're essentially saying that it reduces by it worsens by 5% or 10%. So clearly not a bad trade-off, right? So in the improvement heuristic, we recalculate the minimum travel time only every D steps. We don't do it every step. And likewise, as I described, we look at the time into feasibility to reject certain insertion locations for customers, as we did for the construction heuristic. There are also sort of other things. If you recall, like the compactness and the outliers depended upon the definition, the medians or the median and the median absolute deviation, which are properties of the route. Now, when you're basically trying to insert an unrouted customer, you need to compute this each time. So instead, so you say that, well, you save them, and only when the route changes, you change them. Likewise, if you're looking at a particular route, and if you're looking at a particular route and a particular unrouted customer, if you computed the outlier cost earlier, then you can save the hash of the route, and then if the hash of the route changes, then you basically say that, well, you need to do a recomputation, right? And then, of course, you ought to maintain, because you're looking at nearest neighbors, you maintain a sorted list of like, you maintain the sorted list of distances. There have to be some changes that have to be made, but basically that's the idea. Okay, so we quickly talk about the results. So what you have on the left-hand side is the out-of-the-box solver, and this is our algorithm. And you can see that in here that the routes tend to be more overlapping. They're more non-compact. They're spread out. Here, it's significantly better on the right-hand side, where the routes are more compact. It's like it's also like yeah, there are not as many outliers, and there's less of overlap. And if you actually look at the numbers, you can see that our algorithm basically does better on practically every count. Specifically, the compactness is reduced from 2,900 to 768, and yeah, even the travel time is lower. But in general, there'll be a trade-off, right? Not everything looks like this, but practically every single case you get a better outcome. This is without time windows. We have some cases without time windows. It's a little bit harder to see here. What you see on the left-hand side again is the out-of-the-box solver, and this one is our algorithm. And you can see if you observe closely is that even here there are lots of routes that are spread out. Whereas here it's relatively compact, and in fact, if you dig down into this, if you zoom into this, you'll find the same thing in other regions as well. And then if you look at the cost, you'll see that, well, again, the fairness cost increases in our algorithm. It's relatively more uneven, but then the other things compensate for that in a much bigger way. So you're sort of reducing the overall cost by more than half, right? Great. And this is the end. The set of references. A lot of these are for exact solutions, exact algorithms. Specifically, you might want to use the shrimp and the Solomon paper are things that we've drawn some inspiration from. And yeah, that concludes my talk. Thank you.
Are there questions? There are mic runners around. Raise your hand and they'll come to you. Excuse
me. It's a great talk. So when you do these time calculations, do you take traffic into account?
Correct. So ideally, you would like to, but as far as the algorithm goes, these things, it's an input, right? You give me the pairwise travel time, and I just use that without any further changes to it. So that if you want an accurate result, you need to have traffic data then. Yeah, let me just go to the one appendix slide, which I think is what you might be referring to. Yeah, go on. Yeah.
So you compute the times as a function of distance, or is it using some real world conditions that you have?
Yeah, like in certain cases, we basically query the maps. In certain other cases, we don't. But even there, it's a bit more tricky because, say, for instance, you're doing a route planning at 6 in the morning, and you don't know exactly which customer is going to be visited when, because your span is say between say 7 in the morning to say 2 in the afternoon. Now you don't know which customer is going to be visited a priori when they're going to be visited. The traffic situation changes. So there are those challenges, which is why the slide which I didn't show is to say differentiate between algorithmic performance and the final performance, which where it depends on the accuracy of the input. It's basically if you provide poor, inaccurate input, doesn't matter how great your algorithm is, how well fine-tuned it is, it's still going to get suboptimal results. You're going to get breaches.
Hi, Venkatesh. My question is around the carriers or the vehicles. So, do you factor in anything about the carriers and the vehicles in terms of in your algorithm? And is that the your in-house carrier vehicles, or it's a vendor that you have a tie-up?
Okay, there are two questions, right? I'll definitely answer the first part. Yeah, as far as the vehicles go, like I said, we use a constraint which is the capacity. Right now, what I showed you was just a straightforward thing. That is, each of them has a maximum capacity. It's like 30 shipments, depending on what the context is. Right? Whether in some cases it could be like a three-wheeler, it could be like an auto, or sometimes it's just like a motorbike, right? Now, that need not be the only thing. You can also consider the volumes of these things, right? Volumes of these shipments. And so you have a maximum volume for the entire vehicle that it can carry. And so you sum up the thing. So yes, those things go into the cost function. And then when you're doing the insertion, you take that into account by saying that, okay, you're not going to breach that. The second question is it's a combination. To the best of my knowledge, it's a combination of both in-house as well as like external vendors.
Hey, hi.
Yeah.
So my question is around, do
Can you keep them?
Oh, is it audible? Yeah. So, thank you. So it is around, do you take into consideration like previous routes you have made? So a lot of routes might have a lot of overlapping areas. So are you somehow leveraging that previously computed things that, have been done?
No, we at the moment we are not. Although the idea would be that, for example, with the same issue as traffic, that may be a useful thing to consider. Because however, whatever the maps might give you, it may be useful to look at like what the actual travel times were in a given area, and then use that as a feedback when you're doing future computation. But that's currently not there, but that's definitely part of the idea for going forward. Yeah.
They're at the back. Yeah.
Hi. So I know you. Sorry. Uh, uh, can you give me an example of the running time of your algorithm? I mean, I know you described the complexity.
Could you be a bit louder?
Hi. Sorry. I know you described the complexity of your algorithm, but can you give me an example of your running time for example, 100 nodes or 500 nodes?
Okay, I'll repeat the question. You said what you're asking is that you want, although I gave the complexity symbolically, what's actual runtime in practice, right?
Yeah.
Okay, good. Yeah, so okay, let me give a more concrete example. Say with time windows about say 800 shipments with all of these optimizations, and there's also quite a few other things that is there which I didn't mention, but with all of them there, it takes about say 25-30 minutes to produce the routes. But again, you have to understand that you have to stop the algorithm at some point. You set number of iterations and everything. You set it accordingly so that it produces route. You can, yeah, but that's a
Hello.
concrete
Yeah.
case.
Hi, this is Pavan. So, have you ever tried on leveraging past data? Like pretty much the routes will be repeating like 50% match every day, right? Like 30%, 50% match. So, did you try leveraging any past data?
Yeah, that's kind of similar to the earlier question. No, at the moment we have not. But one thing we do intend to do is look at the traffic, how the traffic patterns are in the different region, and then try and use that.
Okay.
That's the main thing. Because the thing is that even just to continue, one other point is that even if there are two shipments that are different, 2 or 3 shipments, even if 10% shipments that are different on 2 different days, it's not necessarily the case that we should use the same exact pattern there, right? Depends on the other shipments, depends on where the other locations are. So I would think that would be suboptimal, or at least that's my initial stab at it. We can definitely talk about it because I've thought through these things, but yeah, we can definitely.
Hi, great
Yeah,
talk.
yeah.
So when you were talking about inserting a new route or new delivery location, you are assuming that the time windows are somewhat flexible, or are you able to support scheduled delivery versus flexible time windows to optimize this further?
Okay. Yeah, it's a great question. So the question is basically like, am I using these as hard constraints? So everything I talked about today is assuming it's hard constraint. Um, More specifically, if the hard constraint is violated, I don't consider that at all. I just move on to the next point because I only look at feasible solution. So I didn't mention it here. We have worked on it because there are cases where there will be breach, right? And tackling the breach is some kind of a soft time window, which is kind of what you're saying, the flexible thing. And so that's a there's separate heuristics to deal with it. But yes, that's a real world scenario, and yes, we have a way to do it. Although I didn't cover it, but happy to discuss that offline.
Hello.
Any more questions? We still have a few minutes.
Yeah.
Hello. Hello.
Yep. Yes.
I was wondering if you could talk a little bit about all the assumptions you made and how it impacts your final solution.
Great. Yeah. So the assumptions are very is like, first of all, the travel time matrix, right? If your travel time matrix is off, then obviously, and especially if it's off in the earlier stage itself, then all the subsequent things are going to be worse. Now that also is not necessary. It's like it also depends on how much of time window buffers you have at each customer, because you can have wait times. But if it's very, very tight, you're sort of very close to breach, and you have one of these things that are delayed, then yes, that's going to worsen it. The other critical thing, is the location. So there is obviously the geocoding and geospatial intelligence part of it. There are issues over there as well. So again, it's a matter of input accuracy. And so if that is off, then you have a problem. And yet, I mean, like, yeah, that's basically the two primary things. When you come to breaches, there are a few other things that we take into account. But yeah, we sort of, the travel time. And if we don't use travel time, we basically use distance and then a constant speed. The constant speed is obviously a very unrealistic example. So yeah, so those are sort of the assumptions that go into it.
Hi Venkatesh, Archit here. This side.
Oh, hi.
Hi. So my question is, I'm not sure whether you have covered it or not because I joined the talk like a bit later. So the algorithm, as far as I understand, is it mostly works on static data. Like once you have all the timings, if you have all the timings and distances and everything, and then you work on it. So do you also plan to extend, like it's not an extension per se, but do you plan to take it and make it more dynamic in the sense that if the situation changes on the date at runtime, then you also adapt to it?
Yeah, very good question. Yeah. So if I don't know, yeah, you said you joined in the middle. The very second slide or the third slide talked about like how this assumes predetermined shipments and fixed locations, as opposed to say an on-demand delivery system like cab aggregators or something, right? So that's a very clear distinction that I do. But more specifically to the point, yeah, we don't plan to like sort of make changes along the way. That's currently not there in the thing. But maybe one possible thing that could be done is that when you're into the routes and then say the traffic patterns changes, maybe you can run it again for a subset of shipments that have not been delivered yet. But that's still, I would say, still a significant time off. It's not in the medium term at least. There's a bunch of problems to solve here.
Okay.
But
one last question. We will stop the questions. I know everyone's really excited about this. This is a very classical problem and keen to ask. So please hold your questions, grab Venkateshan outside, and keep continuing the discussion. That's